Okay, so first I want to ask if you have any questions about the last times. So if now let us continue. So it's the same topics, separation of variables. So the last time we found, I should write this formula again. We found that, we know that Laplace operator in radial coordinates can be written in this way. So it is dr squared plus, no, let us write the general formula, n minus 1 over r dr plus 1 over r squared. So it is called sometimes Laplacian omega, which means angular Laplacian. And this angular Laplacian for d equals to 2 is just d2 over d phi squared. And for d equals to 3, so I don't have space. It is 1 over sine of theta d over d theta sine of theta d over d theta plus 1 over sine squared of theta squared over d phi squared. So let me tell some general thing. So at the moment we are in the following setting. That we have some some system of commuting operators. And these operators are not only commuting, but they are self-adjoint. Oh, in principle, so we can further add some other coordinates like time, something else. But let's think just about this Laplace operator. So in this, for example, if we consider separation of variables in Cartesian coordinates. So it can be written like Laplacian equals to d over dx squared plus d over dy squared plus d over dz squared, and all of them commute. D over dy squared d over dz squared and the Laplacian all commute. But if we go to case of array and well, we were able to diagonalize all of them using the Fourier transform. But I want to tell that it is actually the general phenomenon that such operators can be diagonalized. So in this case, we have a Laplace operator itself. We also have an operator d over d phi. And we have this Laplacian of omega. So, and the statement is all of them commute. So, is it obvious? So, so it is a kind of a general a general setting. And let's now remember what happens in the finite dimensional case. We have some A1 and so on n such that AI commutes with AJ and all of them are Hermitian. So if it is true, then exists so it is a theorem which we will briefly remember. So if we have such setting, when we have n commuting operators, each of them is a Hermitian, then we can choose such a basis E. You need to use some label. Let us choose this label alpha. So all the operators act on some vector space V. So there exists such a basis as such that all these vectors are eigenvectors for AIs. AI acting on E alpha equals to lambda alpha I E alpha. And these vectors are orthonormal. So the proof of this theorem is very simple, and it will actually be used in the infinite dimensional case as well. Do you remember this theorem? Did you have it anywhere? Well, oh, no. Well, in any case, and by the way, I forgot to tell that this scalar product is half half bilinear. In the sense that some lambda v mu u equals to lambda bar mu v u, and positive definite. So if we have the setting, then we can take some eigenvector of A1, for example. Hmm? The question is, did you see such a theorem anywhere? Ah. Mm-hmm. Ah. So, mm-hmm. Yeah. Sorry, I'll put all this open. Mm. Mm-hmm. Mm. Oh. Maybe it's. Oh, wasn't this one? Yeah, so the proof of this is simple. So, like, we can take some vector which is the eigenvector of A1. Let us take E1 eigenvector. Mm, sorry, I'm not eigenvector. Let us take some V1 uh, eigenspace of A1. It is invariant under the action of all other operators because they commute. Because like A1 times A2V equals to A2 A1V equals to lambda A2V. So if it was eigenvector of A1, then action of A2 on it is still eigenvector of A1, and so on. So it is not surprising, but so in this case, Then we can decompose it as a sum of eigenspaces of all the operators. So V1 can be decomposed as some V1 some in some other index E common eigenspaces of all these operators. So in this way we found and it exists because there can be several arguments for existence of this eigenspace. Like several different proofs, proof one. Because we can solve the equation, a determinant of A1 minus lambda times identity operator has a solution, it has some solution. Also, I forgot to write here that these alphas are real. So we take a solution and then solve equation like A1 minus lambda I on has solution some lambda star. Take this equation times v equals to 0. So it is some vector. So this space is non-empty. But there can be another proof which is better for our infinite dimensional case. So let us consider the following functional of a vector. So what name to choose? Let us call it E of V, which is a scalar product of V times AV over V comma V. So let us consider the variation of this functional. So in this case, it is just a function on a vector space. So d E of V equals to what? 2. Well, let us take here 1/2. So it equals to 1/2 dv times AV V AdV or VV. So Uh, at this moment, we need to use self-adjoint instead of this operator. So so here we use that AV with dV equals to V AdV. So convert as VV squared, and here it is dV times AV minus uh, so um, yeah, like this. And now let us rewrite this equality in the following way. So um, I want to write it as a scalar product of dv with some other vector, and this vector is uh, v times v av minus uh, v minus v av times times v divided by v squared. If you look, so it is a differential of this function e. So if we now ask that this dE equals to 0, it should be, of course, for all dV. Because it is just statement that all derivatives of e are 0. You consider external of this function. So so if this vanishes for all dv's, it means that the only chance for this to be true is that this vector is 0. So AV equals to VAV or VV V. So it tells us that V is the eigenvector. And such eigenvectors always exist because so in this case, we can say that there are even two, at least two such eigenvectors, just from consideration of this function, because so. Because this functional is bounded by some max is greater than this E of V greater than some minimal. So, principle, what I'm saying here, that it is so this function, constant levels of this functions. Constant levels of this function are some ellipsoids, and main directions of this ellipsoids correspond to eigenvectors of A. So. And here we can say that we, for example, normalize this vector to the unit sphere, and we are considering this well, I'm not a good painter, but we have this ellipsoid. And we consider it no, maybe it's a bad explanation. No, it's fine. So we find extremes of of the distance to a point of this ellipsoid, so it's kind of E of V. In the direction given by a vector V, and this extremal values correspond to a main axis of this ellipsoid. This one, and this one in this three-dimensional case. So is it fine? So we can also use this tool to find the eigenvectors one by one. So we can say that V1, lambda 1 is lambda 1 is, for example, a minimum of this vector of E of V. And then etc. But the question is how this procedure goes further. So at this moment, so we actually used self-adjointness of this operator, but we need to use it again. So we know that there is some eigenspace of A1, but there is also a statement that orthogonal complement to this V1 is also invariant under A1 and so on An. So why is it true? Because if some U was orthogonal to V, for all V in V1, then AI of AI times U multiplied by V can be written as U AI dagger, which means a joint operator times V. And if AI dagger is equal to AI, we can rewrite it as lambda, as some lambda I. Well, oh no, sorry, it's not necessary. It is it is an eigenvector of this operator, but we have some other vector AI times V, and it was in V1. Because V1 is invariant under A1 AN. So it is vector in V1, so it is 0. So orthogonal complement is also invariant. and then we can proceed with this recursion and find all the decomposition into the eigenstates. But in this particular case, we can so in this approach, we can say that the first eigenvalue and eigenvector can be found as the minimum on this space, and then we can find a lambda 2, which is a minimum of this energy on the orthogonal complement to this first eigenvector. So orthogonal complement. So this can be done in this way, but for the finite dimensional case, it's in this picture. So now let us try to do the same in the infinite dimensional case.
So in that part to find lambda 3 and so on, we continue taking orthogonals.
We take, so actually if we have several, if this is achieved on some subspace, then we should take orthogonal complement to this subspace. So if you have several eigenvectors with the same eigenvalue, so we should take orthogonal complement to this. But the idea is that we find some eigenspaces of the separator, then we take our orthogonal complement, which is closed, and then we work only on that complement. Yes. So in the finite dimensional case, this procedure terminates just because we run out of vectors. Space is finite dimensional, but in the infinite dimensional space, we should say something else. And namely, we should say that a difference between the vector norm of the difference between any vector and its orthogonal projection to some n-dimensional subspace converges to 0, because because it is what should be done in the Hilbert spaces. So we need some convergence, and this convergence is defined precisely that some vector is some sequence converges to 0 if norm of vector of the sequence converges to 0. But the vector itself as a function can converge to something else. For example, if it has some discontinuities, some jumps in the set of measure 0, then it can still it is still assumed to be 0 in this norm. So okay, so now what happens when we have infinite dimensional space? So let us consider, for example, operator minus I d over dx. which acts on the space of functions L2 of some interval from A to B. So this space, this is a space of square integrable functions on the A interval, and a scalar product is defined like f f and g equals to integral from A to B dx f bar of x g of x. So the standard product. So we should notice that this operator cannot act on any function because in principle we can take this discontinuous everywhere function such that its norm is 0 and it is in this space. And this minus I d over dx acts on continuous functions. And now, what about self-adjointness? We already did this computation actually, but let us consider this difference: f times minus I d over dx g minus I d over dx it is integral from A to B minus I dx. So we can easily check that it is d over dx f of f bar of x g of x. So it is minus I f bar of b g of b minus f bar of a g of a. So we see that everything should be fine except for this boundary terms, because this this difference vanishes up to boundary contributions. To define this operator minus I d over dx, we should actually define the space of functions on which it acts. And this is called the domain of the operator. So actually this minus I d over dx acts on some domain of and well, so oh, I wrote like it acts from this place to itself, but it acts to this L2 of EB. So if we differentiate function, if we differentiate continuous function, it should not necessarily be differentiable after this. So so we fix some subspace of functions and call it domain of this operator. And now we define a domain of the conjugate operators. So it should be defined like follows. So for any f in the domain of for any g in the g in the domain of some operator a, and for any f in the domain of the operator a star, which is the conjugate operator, we should have this equality that f a g equals to a f g, and operator is called self-adjoint. So by definition, when it is a summation, in the sense that a equals to a or star or dagger, I don't know which notation to use, using this notation, and a domain of this operator equals to domain of its conjugate. So maybe let me focus on this definition. This definition actually, so this definition actually defines domain of the conjugate operator if we know domain of the if we fix domain of operator A, because it can be read as follows. So if we fix arbitrary G in domain of A, then all such f's that satisfy this equality form a domain of conjugate operator A dagger. So so in the sense, it is kind of non-commutative definition, because we first change arbitrary G and then say that all vectors that satisfy this equality are in domain of A dagger. And now let us see what it gives in our particular case. So so we need to cancel somehow these two terms. And the most obvious option is to say that domain of A of well, minus I divided dx are functions that vanish from the boundaries. C0 of I will just write C0 so f is in C0 such that f of A equals to f of B equals to 0. But if we do this, then domain of the conjugate operator becomes just C0. So it is just f in C0. We don't need any other conditions because it vanishes due to vanishing of this function in both limits. Well, let me use a different notation here to reflect this fact. So it if you choose such boundary condition, this operator is not self-adjoint. But we see this principle when we ask G to be 0 on some boundary, then F can be arbitrary. So in principle, and in some sense, this space is this space is a little bit smaller, this space is a little bit bigger. So in principle, we can try to ask dx, we can ask this function to vanish only on one boundary, g of a equals to 0. So in this case, oh sorry, it is a conjugate operator here. In this case, domain of conjugate operator will be found by functions that vanish on the different boundary. So they are also different. It's not self-adjoint. And let us consider the last option. Let us say that domain of minus I d over dx is functions g in 0 such that g of d equals to so I forgot if you can do, well, I think we can do this. Phi alpha g of a. So in this case, so alpha is real. In this case, we see that we can ask the same for domain of the conjugate operator, and this terms will just cancel because they have function and conjugate function have opposite phase when we go from one side to another one. And so in this case, the domain is equal to domain of the conjugate operator. So it corresponds to functions on a circle with a non-trivial boundary condition. So it's the only example of boundary conditions for which it is self-adjoint. So this one, but and we actually have an example of such operator. This is this dual already phi. So let me put here minus I to make the self-adjoint. So it is this operator. Because our functions are precisely periodic in phi, so we're in this situation. So now let us go to the second order operators. So it is called Sturm-Liouville theory. So let us consider the following operator. So uh, it can be obtained. So we can either say that it is what is written there. It is the angular part of the Laplace operator. Uh, or we can also introduce the new variable sine cosine of theta equals to x. It is another option. So this hat is what it is dor dx. It is minus angular Laplacian. So So in this case, x is cosine of theta. X is from -1 to 1. P of x is 1 minus x squared. And Q of x is m squared, or 1 minus x squared. Or we could work in the angular coordinate. In this case, we would have an integral w, which is a sine of theta, and this is a precisely integration measure. So, a scalar product is defined as an integral from a to b f bar of x, g of x, w of x, dx. And it is obvious from here that some natural condition for w is w of x is greater than 0. It's one condition. And another condition, I don't know if people always consider this, but it is also very natural and good to ask that this p of x is also greater than 0. In general, probably it is called regular problems. And also, it is convenient to ask that this Q of x is it's not always necessary, but it is better to ask that Q of x is greater than some n for all x in AB, so that it is bounded by some number from below. So we consider such operator, and we want to do precisely the same. We want to find the eigenbasis of it. And use this eigenbase as a basis in the Hilbert space of square integrable functions on this interval from a to b. So the first question we need to study is to ask about self-adjointness, about this L hat. So we want to compute f L hat g minus L hat f g. So this is what? This is the integral from a to b. This term cancels because it is the same in both expressions, and we only have this term with derivatives. So so here it will be minus f bar d over dx f d over dx g p plus g d over dx p d over dx f bar dx. So now we integrate each of these terms by parts and get what on one boundary it is so it is minus p f bar dg over dx plus plus p g df over dx. And if we integrate this by parts, then remaining terms will cancel because we can actually write the remaining terms, at least one of them, maybe for this part. So it is plus integral from a to b df bar over dx p dg over dx dx minus the same term integral from a to b df bar over dx p dg over dx. Yeah. So these are terms coming from this part of expression. And here it is from a to b. And this cancels. And we are left with such expression, which is mm, so people call this Wronskian. P of A, Wronskian of F and G, F and G of A, of B, sorry. Minus P of A on the same Wronskian of A. So we see, and this Wronskian is by definition, so F bar. Wronskian of F and G of X is by definition F prime G minus G prime F. Okay, so this is the difference between operator and its Hermitian conjugate is this expression. And if you want it to be zero, then There are two possible ways to choose boundary conditions. So let me maybe erase this. Uh, So one option is to say that so if this function p vanishes on the boundary, so p of a, so if p of a is 0, then uh, f of a uh, should be finite. And it's enough because the domain of the conjugate operator consists of the same functions, and this part of difference vanishes because just because of this function p of a. And if p of a is different from 0, then mm, we should achieve somehow that Wronskian of mm, f and g vanishes for all functions so this Wronskian of f and g for all at this particular point at a. For all f and g in the domain of L, which is the same as domain of L dagger. So it tells us that f prime of A over f of A is equal to g prime of A over g of A. It means that, well, it's up to vanishing and non-vanishing functions. In principle, we should write it as a bilinear relation, but it can be written in some normal way as a condition that alpha a alpha f prime of a plus beta f of a equals to 0, and the same for g. Alpha g prime of a plus beta g of a is 0. So there are such such generalized boundary condition, which can be the Neumann so So in all this case, this operator will be self-adjoint. And if you look at our operator, which acts on this interval from -1 to 1, then we have this boundary. We have this situation on both boundaries. So this P of x vanishes there. And in some other cases, for example, if you consider if you consider d over dx squared on the interval, then we should impose these boundary conditions on the boundaries, and we actually did this already. So check that problem. Are there any questions about this? So. Okay, so now uh, let us try to repeat this procedure of finding eigenbasis. So I've already raised this function, but remember that we consider this on this functional. In that case, it was functional on the vector space. In our case, it will be functional on the Hilbert space. So. E of f in this case will be the ratio of f L f over f comma f. So we can actually reuse this computation because we need to perform integration by parts. So it can be written as 1 over comma f, and here we have, if we integrate by parts, we will have a p bar of a f prime of a minus p of a minus p of b f bar of b f prime of b plus this integral plus the integral from a to b absolute value of df over dx p of x dx plus and there is this term which I didn't write, but which we will have, of course, plus integral from a to b absolute value of f squared q of x dx. So you see now why I asked this p to be positive, because in this case this operator becomes well, this part becomes a positive definite, and we can say that it is this is greater than 0, and this is greater than some number. So this operator L hat is bounded from below. Its eigenvalues are bounded from below, and we can use this argument to find a minimal eigenvalue. So, so is it fine? So, and also if you talk about this part for non-trivial alpha and beta, then we can write that it is 1 over f f. So here we express f prime in terms of f and get something like p of a beta a over alpha a for absolute value squared plus p of b. Probably this bar is here. No, sorry. So in principle, it's clear that if you want to use this argument about operator bounded from below, we should ask this to be a non-negative. That's it. So, and now we can say that there is some lambda 1, which is minimum of this E of f actually on O2 of AB, but in reality on the functions for which we can compute the separator, so they are they should be piecewise differentiable. So, and there is a corresponding F1. So we get a pair of lambda 1 and F1. So is it fine? So once we have this, we can ask. So mm, so what we did here is we solved the following equation on this L hat acting on f1 equals to lambda 1 f1. And this is some second order equation. The question is, do we have another solution of the second order equation? And to study this question, we should consider, so suppose that we have f1 and f1 tilde. So So suppose that we have another some G1, such that L hat on G1 equals to lambda 1 G1. And now consider the Vronsky of these two solutions. Namely, let us consider d over dx of p of x Vronsky of f1 g1. So I can erase this. So what does it equal to? So in the this one can consist of two terms, and in the first term we get d over dx, so g d over dx p df over dx plus dg over dx p df over dx. It's for the first term. For the second term, we just exchange them. So f d over dx p dg over dx so we see that this cancels, and for these terms we should remember that these functions solve our equation. Namely, it gives so it gives j minus jf q just jfq minus lambda. Let us say that it is, in principle, we can try to consider this expression also for functions with different eigenvalues. So let us write here some lambda f times gf. So, and another term is even the same in this one. It is minus gf fq plus lambda g gf. So, so we see that this cancels, and lambda g minus lambda f gf. So it equals to d over dx p of x around scan of f and g x. So now if lambda f equals to lambda g, then Wronskian of f and g equals constant. And now we should look at the boundary conditions. So suppose that p of a equals to 0. Oh, sorry. P of x times w of equals to constant, this one. So if p of a equals to 0, then it means that the Wronskian of f and g of x is some constant over p of x. Well, so it is true in any case, but if we have this, then there are two possibilities. Either this constant equals to 0, and so f is proportional to g. Another possibility is this, that this constant is not 0. And in this case, g should be singular. And what size g will we get, we can see from this equation. Because if we know f, we know that it behaves like constant, we can solve this first order differential equation for g and find another function. So how it works in general. So if we take some second order differential equation with some boundary conditions, we can ask for some boundary condition on one boundary, and it defines defines, for example, the value of solution, and since the solution, since the equation is linear, we can ask for another initial value to put it to some, equal to some number. So this is fixed. So imagine that we have this interval from A and B. So we define some. So it can be either some value and first derivative, and then we solve this equation. So we get something like this, and then depending on how this other boundary looks like, we can have two kinds of problem. So if p of 0 is 0, then in the most cases this solution will blow up around this boundary. So it will go to infinity. And in order to avoid this, we should choose initial value and eigenvalue of this equation in such a way that it is still regular at the other boundary. So we can see this in this example with Legendre polynomials. I'm planning to tell this explicitly. So this is what happens for such boundary. And if we have if we have P of A is different from 0, then and for example, let us say that f of 0 equals to 0. So f of A equals to 0. And we impose this condition. Then f prime of A, g of A minus f of A and g prime of A of A different from 0 means that g of A is non-zero. So it tells us that this second solution of a differential equation, which in principle exists, will necessarily violate boundary conditions. So the spectrum of this operator, of this one-dimensional operator, is always simple. And also because of this, its eigenfunctions can be chosen, they can be made real. Right? But I have to turn on the light. Oh. So the consequence is that only one, so a spectrum is simple. By the way, before I raised this part about self-adjoint and non-self-adjoint operators, a kind of physical intuition for this is the following: that non-self-adjointness of the operator corresponds to the fact that if we choose this operator as a Hamiltonian of some mechanical system, then a particle described by this Hamiltonian will escape the region which we consider in finite time. So, for example, in this case, it means that Hamiltonian which equals to momentum, it is momentum operator, corresponds to motion with constant speed. And if we put particle on the interval, it will escape in a finite time. But if you put it on a circle, then everything is fine. So it does not escape. If we consider p squared, it means that it is a particle which it is a usual classical particle, and it can reflect from the boundary. So we can ask for this. Like we can put a concrete wall and ask it to stay in this interval. These mixed boundary conditions are a bit trickier, but they can actually be modeled by kind of delta functional potentials inside the writing of these walls. So we can also consider such a mechanical system. And if we add such non-trivial p, which vanishes on the boundaries, then we can transform this potential to something like p squared plus we can like minus d over dx squared, which is quantum mechanical potential, or quantum mechanical momentum, plus some potential. And this situation when p vanishes on the boundaries will correspond to potential with infinite volts, which also means that a particle cannot escape. And if you continue this analogy, there are some pathological examples of non-self-adjoint operators which formally look at least Hermitian. It's just a normal operator, but with some strange potential. So in all these cases, so as far as I know, this potential is singular and can go to minus infinity. And quantum mechanical intuition is that in this case, a particle can either fall on a center of potential or go to infinity in finite time. For example, potential minus x force is a classical mechanical potential which allows to reach infinity in finite time, and it is also an example of non-self-adjoint quantum mechanical potential. So there is such kind of intuition, but if we work with something nice like this operator, then we don't have such problems. We should not think about this too much. So once we have this, so we know that we were able to find the minimum of this functional. And let us repeat this procedure as in the classical, as in the finite dimensional case. So so this lambda 2 can be found as a minimum on the orthogonal complement to F1 of E of F. And of course, so this orthogonal complement is also enclosed with respect to L hat. So if you find the minimum, then it will correspond to some other eigenvalue and eigenvector of L hat. And since we live in the orthogonal complement, it means that this vector should definitely have a bigger eigenvalue. So than lambda 1. So it should be strictly bigger than lambda 1. So and so on. So in this case, we get lambda 1 f1, 1, lambda 2 f2. So lambda 3 should be minimum on the over the orthogonal complement of f1, f2. Here of f. So in this way, we get this system of eigenfunctions. And there is a theorem which I will probably prove the next time because this 3 minutes. 5 minutes. So if you take some vector phi, well, actually, maybe we should ask for something or not. Well, maybe better to ask it to be no, maybe just in L2. Yes. But we will see later. Then a norm of the limit phi. So if you now define orthogonal projections of this f, fn equals to sum from k equals to 1 to n phi phi over phi phi phi. Then limit when n goes to infinity of this difference phi minus phi n equals to 0. So the eigenfunctions of L from a basis in the Hilbert space of function on this interval. With well, with this norm, but it is the same for any W. So
Mhm. So for each eigenvalue, we found one eigenfunction, right?
yes.
But might be some eigenvalues with this equation. So
Oh, but
is this bigger than 1?
no, but this is precisely what we checked. So it is what we did here. We know that it's second order operator. So it can. So formally it has two solutions for each eigenvalue. But this complementary solution necessarily breaks the boundary conditions. So. So for example, on the if we work on the interval with operator just d2 or dx squared, one solution is sine, which vanishes on two boundaries, and another solution is cosine, which breaks this boundary conditions.
So for this reason, each eigenvalue is strictly bigger than the previous one because we
Yes.
don't have any. Okay.
Yes, and actually, well, probably this is probably I can say it now. and it will be useful. We also have that a limit when n goes to infinity of and then is infinity. The simple argument for this is the following. If we take to prove this, we just need to know that the solution that this equation has solutions for arbitrary big lambda, and a simple argument for this equation L hat f equals to lambda f. The argument is that for example, if we take p equals to 1, then it tells like d minus d two over dx squared plus q over w f equals to lambda n maybe, and also w equals to 1 plus qf. So the simple argument that when we send the lambda to infinity, we can neglect this potential term, and this equation looks like minus d over d2 over dx squared equals to lambda n f. So approximately, so f is proportional to sine of square root of lambda n x. And this equation has solutions. So if you now ask, so we have f of 0 equals to 0, and the equation that f of, for example, 1 equals to 0 is equivalent to square root of lambda n times pi equals to n. So this eigenvalues grow quadratically with n. And we actually saw this in this Legendre polynomial case, because because the eigenvalues were growing like L plus 1, which is L squared. So it is a typical situation for such problems on finite intervals. So, do you have any questions about this?
We had a reading one and oral one. So we had a reading exam and an oral exam.
Sorry, could you say it again?
So about the exam, we had a reading exam and an oral exam.
Yes. So
and the oral one is mandatory. Because there are some courses that optional.
so but how does it usually work? Oh, maybe it's hard to say that it is mandatory, because in any case I would like to discuss solutions. For example, if you could not solve some problems during the written exam, you can think how to do them at home and tell this the oral exam. So I think.
So the oral is about So the oral exam is about the solution that is not
No, I will also have some general questions, but the important part will be a discussion of solutions. So, but if you write a written exam good enough, then I will not have a lot of questions. So probably I'll give some big number of problems for the written exam, but say that you need to solve like half of them or two-thirds. Think about this. And by the way, how long are usually written exams? Hmm?
Depends on the quantity of exercise.
Ah, no, but
For analysis, we have 3 hours, I think, and also for jump,
ah,
3 hours. For like 4 or 5 exercises. Yes.
ah,
Yes. We have 4 or 5 exercises in 2.5 hours or 3 hours.
ah. I see. So, uh,
Yeah, it depends on the exam. Like some were a bit more technical, so fewer exercises.
mm. But here not more than three usually, right? Or not? There are at the University of Trieste or CISA there are no exams longer than 3 hours, right? Ah. Mhm.
Also, this is our first year with CISA, so we don't know exactly
Ah.
but I think that
Yeah, for me it's also the first year. So, yeah. Okay, thanks for your attention. See you on Thursday.
so on Thursday at 11
Yes,
Okay.
yes.
So 11, 1, and 2 for
Mhm.